All right. Hello, everyone. My name is Richard Foster. I will be presenting on the mathematical model of asynchronous respiratory mechanics, specifically of the preterm infant. I conducted this research under the mentorship of Dr. Fix at VCU. Let's go ahead and get started. Right. So the preterm infant, typically born at 28 weeks gestation, suffers from a high compliant or floppy chest wall and low alveolar surfactant levels. This means that during spontaneous inspiration, instead of the chest wall expanding, the chest wall instead visibly falls. This obviously leads to a variety of problems. It can lead to progressive lung volume loss and eventual respiratory distress in the preterm infant. And interestingly, it creates this asynchronous ribcage and abdominal behavior. So during spontaneous inspiration, or in other words, again, the beginning of a breathing cycle, the ribcage and abdomen are supposed to move in sync with one another. They both expand. However, in the preterm infant, the ribcage falls and the abdomen continues to expand, whereas during spontaneous expiration, the ribcage expands controversially, or contradictorily, I guess you could say, and the abdomen falls instead. So we get this kind of asynchronous behavior between the two of them. Now, while studies or controlled experiments on this vulnerable population are not necessarily ethically encouraged, researchers in the past have used mechanics models or computational models to study the phenomena that occurs in the preterm infant. So our very own Dr. Fix constructed a model in 2018 that studies the progressive lung volume loss of the preterm infant, and it treats the chest wall as one compliant compartment. However, the model does not adequately describe this asynchronous or even paradoxical behavior that we tend to see in the preterm infant. So the specific aim of this study is to better model asynchrony in the preterm infant respiratory system by constructing a computational model that incorporates for independent ribcage and abdominal compartment representation. And I'll be discussing what all that means later. So in this model, values of interest are dynamical with respect to time. We have pressure, volume, and volumetric flow rate. And with volumetric flow rate here, the dot representation on top of the V just essentially stands for a time derivative. So pressures are measured relative to atmospheric pressure. So we can have both zero and negative pressures in our model. They are measured in terms of centimeters of water. Volumes are measured in milliliters, and the volumetric flow rate is obviously measured in milliliters per second. Pressures, especially transmural pressure gradients, occur across boundaries and between two compartments I and J, and they are measured as the difference of the measured pressures in both compartments. So certain transmural pressures that some people might be familiar with include a transpulmonary pressure, which is the change in, or the transmural pressure between the lungs and the pleural space surrounding the lungs. We also have the transthoracic pressure, which is the difference in the pressure between the pleural space and the body surface. So those are just a few examples that we might be working with in this model. So in this model, if a compartment I has elastic properties, so when we think of a compartment with elastic properties, we tend to think of the lungs, the chest wall, the rib cage, the abdomen. All of those compartments are given an associated compliance, C. And when I say compliance, I mean a change in volume due to a change in transmural pressure. So we can think of this as a kind of balloon. If we put a balloon out into like a little box and we take the air out of the box to create a kind of vacuum, then the air already in the balloon wants to expand to accommodate this change in pressure. So it is defined mathematically as the derivative of the compartmental volume with respect to transmural pressure. And we can use a change of variables with respect to time here to make both of these states with respect to time, I guess. You have a change in volume with respect to time and a change in transmural pressure with respect to time as well. So here is the electrical analog of our model. We have 5 compliant compartments and we have 6 resistances. The compliant compartments are the collapsible airways, the alveoli, the viscoelastic structure of the lung, the rib cage and the abdomen. Previously, Dr. Fix constructed the model such that the rib cage and abdomen were just one compliant structure, which was the chest wall. But in this model, we have partitioned those two to better analyze the asynchronous movement between the two. There are three airflow dependent resistances that's shown here on the left, and we have three tissue related resistances rather than airflow related in the model as well. We have two driving pressures here that we'll be discussing later, PIC and PDI instead of just one. And this model essentially expands, as I said earlier, on the model presented by Dr. Fix, and we'll be looking at. So now we have an electrical analog. What would be really nice is if we could get some equations from this. So Ohm's law can be used, or at least the pressure volume analog of Ohm's law can be used to acquire some general relationships. So Ohm's law states that for any electrical circuit, the current I is directly proportional to the voltage E and is inversely proportional to the resistance R. This is familiar for people who have taken an engineering class or a science class or something like that. So in the pressure volume analog of the circuit, current refers to airflow, which is represented as V dot, and voltage refers to pressure, P. So using Ohm's law, or at least the pressure volume analog of Ohm's law, and Kirchhoff's voltage law, represented here, which states that the algebraic sums of all voltage drops or pressure drops in any closed circuit is equal to 0. We can construct these four equations here because there are four closed loops in the current model. So the first three come from Dr. Fix's previous model, and the last one comes from our current model. So using these loop equations and the definition of compliance, we can create the following system of differential equations. Again, the first four were from Dr. Fix's previous model, whereas the fifth was added because we partitioned the chest wall compartment. So now we're going to move into the section that I did most of my work on. So our figure, the electrical analog, shows that the capacitors representing the ribcage and abdominal compliances are electrically in parallel with one another. Circuit laws state that these capacitors add directly because they are in parallel, which means that the ribcage and abdominal pressure volume slopes must add because that is the definition of compliance. It's the change in volume with respect to pressure. However, there's a problem. The ribcage and abdominal compartments both share a residual volume left in the respiratory system at end expiration. So if we were to split up the chest wall compartment, which only has one residual volume, into two, and add them back up to the chest wall compartment, we would essentially be adding up a residual volume twice, unless we were to divide the residual volume some way, and not a lot of literature discusses how to divide this residual volume between the two compartments. So our question is, how do we split the chest wall pressure volume curve into two parts such that they sum back to the original without doubling this residual volume? So what we can do is create these pressure volume curves with respect to percent vital capacity instead of absolute volumetric units. At 100% vital capacity, we are at total lung capacity, which is the maximum amount of air that can be held in the respiratory system. Whereas when we're at 0% vital capacity, we are at residual volume, which is the volume left in the respiratory system after end expiration. So this figure is from a study conducted in 1968. This is the most recent paper that we could find with this kind of information. The researchers conducted empirical measurements of the preterm infants' ribcage and abdominal compliances, or their pressure volume data, I guess you could say. The function with closed dots, the one on top of the other, is the pressure volume relationship of the ribcage, whereas the function with open dots on the bottom is the pressure volume relationship of the abdomen, and is measured against percent vital capacity here instead of absolute volumetric units. So to interpolate these points, actually we use plot digitizer to extract the points from the graph, and then we use this interpolating polynomial, the soft plus function, to interpolate the second and last points extracted from the figure. So this figure here is still in terms of percent vital capacity, but we have these two interpolated functions here, one for the rib cage, one for the abdomen. And we incorporated these into our model. So now we have some nice compliance curves for our ribcage and abdomen that add back up component-wise to the chest wall compliance without adding a residual volume twice. So we evaded that problem. And these are the equations associated for the ribcage and abdominal volumes with respect to pressure. So now we're going to talk about our driving functions, PDI and PIC. So previously in Dr. Fix's model, we had one pressure generator instead of two. And since we divided the chest wall compartment into 2 separate compartments, that meant we had to divide the pressure generator as well. So the diaphragm was attributed to the abdomen compartment, and the intercostal muscle pressure generator was given or attributed to the intercostal muscles, or the rib cage. That's what I meant to say. So we use this parameter called pfrac as a way to distribute the original muscle generator function across the 2 pressure generators, or across the 2 compartments. So when pfrac is equal to 0.5, it is equally distributed amongst the diaphragm and intercostal muscles. Whereas when it's 0.2, it is more so attributed to the intercostal muscles. And when it's 0.8, it is more attributed to the diaphragm. So now here's our phase portrait analysis. This is essentially what we were working up to. We wanted to see if there was a kind of asynchrony between the 2 compartments, the ribcage and abdominal compartments. So when pfrac is equal to 0.5, that means that the driving functions were distributed equally. There exists almost no asynchrony between the 2 compartments. All these figures are measured as the volumes of the abdomen versus the volumes of the ribcage. However, when pfrac is when pmus, the muscle generator, the original muscle generator, is muscle pressure generator, excuse me, is unequally distributed amongst the diaphragm and intercostal muscles, then we get to see a little bit of asynchrony between the rib cage and abdomen. Especially when pfrac is equal to 0.2, we see almost a kind of 90-degree amount of or level of asynchrony between the 2 compartments. So there are potential areas for this model. For model innovation. So first, we would need to compare these results that we have here, which is for a high compliance chest wall, versus a low compliance chest wall that we haven't studied yet with this model, at least. And then we need to consult with literature to determine physiological relevance of these results. And then we would need to determine physiologically relevant values for RRC and RAB. So there's a lot that we can improve with this. Because of COVID, our progress was kind of limited. So we're still working on this. It's a preliminary model, but I'm very proud of what we have done so far. I would personally like to thank Dr. Fix at VCU for granting me this opportunity and privilege of conducting research on this topic with her. And I'd also like to thank Herbert Hill at VCU for granting me the honor of becoming an undergraduate summer research fellow. So that is basically it. I hope you all enjoyed, and I will leave it up to the audience to answer any questions that they have about this research. Thank you so much.